Hello and welcome. Today we are going to be talking about sets, subsets, and some set operations. It's a lot of S's. Sorry. All right, let's get going. First of all, a set is just a collection of people, places, and things. And the things that make up the sets are called the elements of the set. There is a symbol for that, and it looks like this. I know it might be a little bit hard to see. When you make that, it's almost like the letter C and then a little line through it, or kind of a funny looking E, which is great because it stands for element. Now, a set can be thought of as some type of a container with the objects inside it. The container can either be physical, such as a box, like holding things, or it could be abstract, more like a list. Okay, so maybe symbols, ideas, etc. Now, a lot of people, when they think of sets and subsets, especially in a math class, think specifically of numbers. So let's talk about some of the more famous number sets that we have. First of all, the natural numbers. Now, the natural numbers are, if I were to say, hey, start counting, well, most people would start at 1. And so the natural numbers do start at 1. 1, 2, 3, dot, dot, dot. This is the set of natural numbers, and sometimes you'll see people use kind of like a funny N, a capital N with a double bar in it, something like that. So in math, whenever we use these special letters where we put that double bar, that's saying it's a set of numbers. The naturals, they're the numbers you naturally start counting at. The whole numbers have all the natural numbers in them, but they also have the number 0, the one that looks like a whole, if you will. The next set of numbers that we're going to look at are called the integers. Now, the integers are all of the natural numbers. They keep going forever that way. They also have the whole numbers, so 0, but they also go the other way, like that. So the integers are all of the natural numbers and their opposites along with 0. There is a symbol that we use for the integers as well. We use a capital Z. There's not really one for whole numbers. Sometimes you see people use W, but it's not really as common. Z seems kind of weird. I think if I remember right, it goes back to the German word Zahlen, which just means numbers. And there's been a lot of famous German mathematicians that studied sets and number theory. The next one that we're going to look at is the rational numbers. P over Q, where Q is not equal to 0. Now, rational means fractional. Any number that can be written as a fraction. So for example, even all the numbers that we've had so far, like the number 1 could actually be written as 1 over 1, or the number 2 could be written as 2 over 1. The number 3 could be written as 3 over 1. So in other words, all of the natural numbers are also rational. All of the whole numbers are also rational, and so on. But also the fractional numbers or the rationals could also be numbers like this, 2/3. They could be a number like 3/4. They could be a number like -7. Any number that could be written as a fraction. Now, also repeating decimals. So numbers like 0.3333 forever, well, that's actually equal to 1/3. We can take any number that has a repeating portion to it, 0.178 with a repeating over that, that's like 0.1787878, etc., where you just keep repeating that. These can be written as a fraction. And if you're not quite so sure about it, there are ways to do that. That's not covered in this lesson, but just as kind of proof of that, we can take and show you that if you take 59 divided by 330, there we go, you get 0.178787878, and I know that ends in 88, but that's just Desmos rounding this for us. So any number that has a repeating decimal can also be written as a fraction and is therefore rational. I don't know if you noticed, but it kind of seemed like all of these numbers, as we went this way, were subsets of each other. The naturals they were like smaller than the whole numbers and they were completely contained. And then the whole numbers were completely contained in the integers, and the integers are contained in the rationals. And yeah, that is true. So if you noticed that, that's great. In fact, some people like to make what maybe almost like a Venn diagram. I'm gonna make a little visual like this, where we say, you know what, these are the naturals. And then slightly bigger than the naturals are the wholes. In fact, they're all the same numbers, but the wholes also have 0. And then you can see we have the integers. All of the whole numbers are completely contained within the integers. It's just that they have more. It's all of the whole numbers and all of the opposites. And then we also have all of the rational numbers. Any number that can be written as a fraction is rational. So rationals contain all of the integers along with all of those other ones. Now, there's also other numbers that we haven't covered yet. Those are the irrational numbers. These are decimals that are non-terminating and non-repeating. These are numbers very famous like pi or the square root of 2, the square root of 3. Think about this. The square root of 4, that's equal to 2. So square root of 4 would not be irrational, right? So we can't just say all square roots. What we would say then is like all of the square roots that aren't perfect squares. Okay. What can't be simplified down to rational. There's also some other numbers. There's a very famous number e. There's plenty of irrational numbers. In fact, there's a lot of them. And you'll notice earlier I said like, oh, the naturals seem to be just a little bit smaller than the wholes and a little bit smaller than the integers. Getting into size gets a little complicated, so I'm just going to keep it easy with what I said, but also with the understanding that that does get a little complicated when we start talking about sizes of infinity. That's not what we're addressing here today. Real numbers, on the other hand, are what we get when we combine all of the rationals and all of the irrationals. Because you see, what we have over here where the naturals are a part of the wholes and they're a part of the integers, then we also have the irrationals. The irrationals are completely separate from those other two. So we have the rationals, which have all of these other numbers inside of them, and then we have the irrationals, and they are completely separate. And when you put those two together, that's when you get the real numbers. Okay. The order of the elements in a set doesn't matter. If I wanted to talk about the naturals, I could say 2, 3, 7, 4, 1, but that gets really complicated. Okay, so with numbers, it is best to put them in order, but we don't always have to be dealing with numbers when we're talking about sets. So the order doesn't matter. A well-defined set means that all the elements are clearly identifiable. If I were to say the set of the best hamburger places in Phoenix, well, that's more of an opinion and it's not well defined. It's not something that just everyone would be able to figure out very easily. If I said the set of the 50 states in the United States, that's very easy to find. The set of the presidents of the United States, like there's a set list and everybody agrees and it's easy to understand. That's what well-defined means. I hope that's well-defined enough. A set can be either finite, like some of those examples I gave, the set of states, the set of presidents, etc., or it can be infinite, right? The set of the natural numbers, that's infinite. If I said the set of natural numbers less than 10, that would be finite. Okay, finite means there's some specific number that you can count to and you can get to the end. Let's go ahead and look at a few examples and decide whether some sets are well defined or not. The students in this class. Well, you and I aren't exactly in a class right now, but if you were in a classroom, a math class specifically, yes, we could have a well-defined set, meaning everyone that's in this class could look around and theoretically make a list, and it's all the same list. It's everyone in this class. The set of best students in the class, now this is not well defined. Anything that is opinion would not be well defined. Let's label these whether they're infinite or finite. The set of integers between 1 and 10. Well, if I wanted to make a list of integers, so I have a set of integers, and I want the set of integers between 1 and 10. Now, when we say between 1 and 10, I'm actually going to be excluding it. That means I'm going to be going from here to there, because between 1 and 10 is exclusive language. So that would be the numbers 2, 3, 4, 5, 6, 7, 8, 9. Those are all the numbers that are between 1 and 10 that are integers. You'll notice that I started out with all the integers, right? From negative infinity all the way up to positive infinity. And then I took just a small little subset of those, 2, 3, 4, 5, 6, 7, 8, 9. So are they countable? Yes. I just counted them, right? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them. I realize it goes from 2 to 9, but there are 8. And that makes these finite. What about the set of real numbers between 0 and 1? Well, remember, the real numbers, that's basically like almost every number you can think of. Now, you might have had other classes in the past where they talked about what are called complex numbers or imaginary numbers. But in general, in common society, not in nerdy math conversations, pretty much every number you can think of is a real number. All the fractions, all the negative numbers, the zeros, even the pi and the e, like those are also real. So when we start talking about the set of real numbers between 0 and 1, like I have the number 0 and I have the number 1. Well, I know that 0.5, that's 1. So is 0.75, that's 1. So is 0.99999. Well, and there's a number in between that. And so is the square root of 2 over 2. You know, like there's a lot of them. And in fact, there's infinitely many. Any number that you name, I can name some number that's smaller than that, but still greater than 0, unless you name 0. So if you name any number greater than 0, I could pick a number between that and 0. There's infinitely many. This is definitely an infinite set. Okay. Let's keep going and talk more about sets that are finite and infinite. If a set is finite, then the number of elements is called its cardinality of the set. The cardinality, or the cardinal number of the set, we would just maybe write it like this even. We just say n of a. There's some other things that we can do, and when we start talking about sizes of infinity, we use an aleph symbol, but that's not for us today. A set without any elements or a cardinal number of 0 is called the null or the empty set. And it's also denoted by, looks like I might have erased it. We can either say this symbol, or sometimes you'll just see a set of empty brackets. Now, I do want to point out this symbol is not the same thing as 0. This symbol is the null symbol, and it means the empty set, okay? So it's not a 0. If you are in the habit of writing your zeros with a slash through them, me as a math teacher, that's tough for me to grade, but it's up to you, I guess. Just know that in math, when we put this circle and a slash through it like that, that means the null set or the empty set. And one of the reasons why those are not the same thing is because if you are up north and it's very cold outside, you could say it's 0 degrees outside, but you would not say that it's null degrees outside. Okay, so that's why those are not the same. Please don't treat them as the same. I don't care personally if you use the null symbol or if you use empty brackets. They both have their uses, and just be aware that some authors prefer one or some teachers prefer one over the other. Let's identify the cardinality of each set. So the set of days of the week, right? Um, there is a couple ways I could do this. I do want to show you my notation up there. If I were to say, let A be the days of the week, then I might ask this, n of A is equal to, and then this is just how big is the set. That's what the cardinality is referring to, is how many elements are there in that set. Well, the days of the week are Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So there are 7 days of the week. We're not trying to be tricky and say like, oh, don't forget about today and tomorrow. And, no. Just 7 days in a week. That's it. Set A is the numbers 15, 16, 17, and 18. So I might say n of A is what? Well, I would identify this and say it's 15, 16, 17, and 18. So its cardinality is 4. The size of this set is 4. Our next one here says n of B, or the cardinality of set B. Notice that set B is the empty set. Remember, that means it's a set that has no elements in it. So n of B is actually equal to 0. The size of the empty set, the cardinality of the empty set, is 0. Please don't put null. Okay, please use 0, because this is where we're saying it is an actual quantity. It's the quantity of 0. The set of natural numbers, if we want to write these in roster form, and then we're going to list them using braces. So there's a number of ways that we can do this. First of all, we just have a description. And what we want to do is write this in roster form. So a roster is a list. So I'll start by putting a brace, and then I'm going to start with the first natural number, which is 1. And now I need to establish a pattern. Typically 3 numbers is enough to establish a pattern as long as it's clear, and then we'll close it up with a brace. This is a way of writing the natural numbers in roster form. The ... just means keep going with that pattern. What about the set of integers greater than -2? So I know that the set of integers go forever in both directions. They include the negatives and the positives. But because we want greater than -2, I can start out by writing -2, -1, 0, and I'm going to put just a couple more on here just to make sure that my pattern is very clear. This would be the set of integers that are greater than -2, except I made a mistake. So because I want greater than -2, I wouldn't actually include -2. I know I could edit that out, but I don't want to, because look, I make mistakes. And that was one of them. We caught it. So greater than -2 means we don't start at -2. We actually want the next number bigger than that. Let's go on. The set of integers between -4 and 2. Notice this word between. This is exclusive language. It means that we're not going to include those end values. If I wanted to include them, I might say the set of integers between -4 and 2 inclusive, in which case it would be -4, -3, -2, -1, 0, 1, and 2. This would be the set of integers between -4 and 2 inclusive, but because we want between -4 and 2, between means I'm not doing that, and I'm not doing that. So what we have left here would be our answer. The set of integers between -4 and 2 is -3, -2, -1, 0, 1. The set of months beginning with the letter M. So I would kind of go through these in my head and I would just start listing all the months of the year. January, nope, February, March, there's my first one. April, May, yes. June, July, August, September, October, November, December. Boy, I hope I didn't miss any. That would be very embarrassing. Represent the set containing the states that border the Pacific Ocean using roster form. So, first of all, roster form. That means that I'm making a list. It also means that I'm going to start my list with a set of parentheses, and now I just need to identify those states. If you know them, great. I'm pretty sure I know them. We have California. We have Washington. And we have Oregon. Now, I am going to say, I actually don't think we have them all. I initially put that there, California, Washington, and Oregon, but I think there's actually a few more states that border the Pacific Ocean or that share a border with the Pacific Ocean. It's not ones that we think about very often, but Alaska and even Hawaii. I'm going to put HI because I'm really bad at spelling. Hi. So sometimes questions are a little unclear, but I think that all 5 of these states actually have part of their border touching the Pacific Ocean. So I feel pretty good about this. If this had said represent the set of states in the lower 48 states, right? Then we would have only done California, Washington, and Oregon. All right, let's keep going here. Set A is a subset of set B if every element in set A is also an element in set B. So a picture of what that might look like, I know we haven't done much with Venn diagrams before, but what that might look like is if we have, this is set B, and if set A is contained completely inside of B, then A is a subset of B. In this case, A is actually a proper subset of B because it's smaller. Back up to our number sets from before, we could say that if B is the whole numbers and A is the naturals, then A is a proper subset of B because every element in the naturals is also in the wholes and it is smaller, sort of, because it doesn't have 0. The symbol for a proper subset is this. It's almost like a less than symbol, but not quite. And you do almost want to treat it that way. Like I would say over here that A is a proper subset of B, kind of like in the same way that I can say A is less than B. So if you treat that kind of like that, you should be pretty good. They do take a little bit of practice, and there's always some very niche, tricky things with subsets and proper subsets. An improper subset can actually be equal to the original. So it's possible to have 2 sets that are exactly the same. And we have some examples down here in a little bit, but let's say that that's also set C. Well, C is a subset of B, it's just not a proper subset. We'll look at some examples in a minute. The symbol for that is kind of like what we just did before. And in fact, you can treat it kind of like this less than or equal to sign. So C is a subset of B because it's less than or equal to. Again, that's not exactly how it works, but it's kind of close. That's how I always remembered it anyways, and so I wanted to share that with you. Let's look here. We've got 5 different sets that we are given. We have set A, set B, C, D, and E. Those are the sets that we're going to be looking at as we start to compare these. Here on number 9, this says A is a subset of B. Are all the elements in A, do they all come from B? Yeah, it does. This looks to be like it's a true statement. In fact, I'm going to write them here, and we'll say that B is 1, 3, and 5. And so that's set B. And set A is 1 and 3. I could go something like this. Notice that set A is contained completely within set B. So yes, this is true. You can also do this by writing the numbers out and then identifying that set A is 1 and 3 right here. Yep, that's completely contained inside of B. So yes, A is a subset. It's less than or equal to. It's not equal to it, but it is in fact less than. The next one is B is a subset of A. Well, are all the elements from B contained completely inside of A? No, we just did a thing like this. If I say that A is equal to 1 and 3, and I try to circle B, I also have to have the number 5 there. 5 is in B, but it's not in A. So therefore, this is not true. In fact, we would probably write this in a slightly different way. Like the question says, is it true? No, it's not. A mathematical way of writing this would actually be to just put a slash through it. Say B is not a subset of A. Number 11 says C is a proper subset of D. Notice that we don't have this line under here this time. That's how we know that this right here is proper subset. And that means that it actually needs to be smaller. Again, I use that word a little bit loosely, but there needs to be fewer elements. There actually has to be elements. So if I look at C, C is 1, 1, 3, 5, 7. And D is also 1, 3, 5, 7. Notice they're the same size. So I can tell that it's not true to say a proper subset. A proper subset has to actually be smaller. First of all the elements from C do come from D, so the first part of our definition is good. Everything from C comes from D. The problem is that C has to actually be smaller, and it's not, so this is not true. What we might even say is C is not a proper subset of D. The next one is the empty set is a subset of C. Well, here's how we can kind of do this visually. C is 1, 3, 5, 7. And the empty set is a set with no elements in it. So I could even kind of just be like, hey, look, I circled something that had no elements. Is this the right way? Not necessarily. But the empty set is a subset of all sets. The empty set, the set with nothing in it, is a subset of every set. That's just how it goes. Think of it like this as well. Maybe I have 2 friends that I could take to Disneyland. I could choose to take Bill. I could choose to take Chris. I could choose to take Bill and Chris. But I could also choose to take neither of them, and I could go to Disneyland by myself, right? That's the empty set. So the empty set is a subset of every set. This one is true. Lastly, E is a proper subset of A. Right? I'm going to make a little note here. This is proper subset, and it needs to actually be smaller. So when I look at E, I see that E is just 3. Oh. And when I look over at my set A, I see that A is 1 and 3. Okay. Now, does every element from E come from A? Yes. E only has 3, and A also has that. And is E smaller than A? Yes. So this is true. E is a proper subset of A. Visually, with what's called a Venn diagram, I could even make it look something like this. There's my set A. There's my set E. Notice that 1 and 3, they are a part of A, and then contained completely inside of A is the number 3. So 3 is a proper subset, or the set E is a proper subset of A. Now, how many subsets can a set have? This gets into something called counting, which I know we're in a math class, so of course we know how to count. Well, there's a very specific kind of counting. Every element in a set has either two possible states. It's either in the subset or it's not. A finite set with k elements has exactly 2 to the k subsets in it. See, I always like thinking of this like making pizza. When you make your pizza, you have to decide every topping. It can either go on the pizza or it stays off the pizza. And so if you have several toppings, you really just have 2 to the however many toppings you have power. So if you have 5 toppings, it'd be 2 to the 5th power. Let's go ahead and look at Esme here. She wants to grab a snack of Greek yogurt from the fridge. If the set T contains her toppings, how many different options does Esme have for dressing her yogurt? She has, let's count them. She has peanut butter, that's 1, granola, blueberries, raspberries, strawberries, hazelnut, and cashews. So because she has 7 possible toppings for her to put on her yogurt, she has 2 to the 7th power number of possibilities. We're not going to list them all out because I believe that's 128 possible ways of eating her yogurt. Right? For example, she could put on peanut butter and granola. That's one possible way. She could put on just peanut butter. That's one of the ways. She could put on peanut butter, raspberries, and strawberries. That's one of the ways. She could put on all of them. That's one of the ways. Right? There's a lot of them. And in fact, the one that most people tend to forget in my experience is the one where she doesn't put any of them on. She has just plain yogurt. She's still going to eat the yogurt. That is one of them. But if you had to list every possible way to do this, many people do forget that that plain option, the one without any toppings at all, is still an option. After finishing his undergraduate degree, Jacoby plans to do one or more of the following: apply for a job, apply for a master's program, or apply for a CERT program. In how many different ways can Jacoby send out his applications? Well, he's going to send them all out. And so what we have here is we have 3 possibilities, and this will be 2 to the 3rd power. That's 8. In other words, he could apply for a job, a master's program, or a CERT program. He could apply for all 3 of them, right? He could apply for a job and a master's program, or he could apply for a job and a CERT program, or a master's and a cert program. These are all the ways that he could apply for 2 of them. Of course, he could just apply for a job. He could only apply for a master's program. And maybe he's decided, I don't want to do the others. I only want to do a cert program. Lastly, he could even choose to apply for none of them. He'd be like, you know what? I changed my mind. He plans to do one or more of the following. So you know what? I actually need to go back and change my answer around because this one is not an option. Like if we said, how many ways could he do all of these and it didn't have this, then there would be 8. The problem is he says he is going to do one of them, one or more. So that means that this one is not an option. Maybe he has a parent at home and said, you have to do at least one of these. So he can't choose to not apply to anything in this scenario. Okay. So notice the difference between our number 14, where Esme could choose to not put any toppings on. And in number 15, it says Jacoby is definitely going to do at least one or more. And because of that, the choice where he does none of them, that's not an option. And that's why there's actually going to be 7 instead of 8. A set containing all the elements for a topic is called the universal set. And that set is denoted with just a big capital U. The intersection of the 2 sets is the set containing all the elements that are common to both sets. The intersection of A and B is denoted like this: A intersect B. That symbol right there, it looks kind of like an N, intersection. 2 sets are said to be mutually exclusive if their intersection is empty. If there is no overlap between sets A and B, then those sets are mutually exclusive from each other. Okay. So let's say all of the people that are in nursery school or preschool, maybe these are my preschool people. And then let's also have another set of people who are retired. Notice there is no overlap. There's no one in preschool. There's no one attending preschool who is also retired. There's no overlap. Those sets are mutually exclusive from each other. The union of 2 sets is the set containing all of the elements that are in either of the 2 sets. So let's go back and we'll make another Venn diagram real quick. In this particular Venn diagram, you can see that in my set A, I have 2 numbers. I have 1 and 2. And in my set B, I have 2 different numbers. Well, I have 2 numbers. I have a 2 and a 3. It just so happens that 2 belongs in both sets. So 2 would be in the intersection of these 2. In other words, back up to what we did a minute ago, A intersect B would actually be the number 2. For the union is actually the word or. In A or B. Anything in A or anything in B. A union B in this case is all the elements in A along with all the elements in B. But we're not going to write the number 2 twice. Okay, that's we don't count it twice. It's in both sets. There it is. So the union is just when you combine the 2 sets. The complement of a set is the set containing all the elements from the universal set that are not in the elements of the given set. Notice that, let's look at set A, for instance. Set A has 1 and 2 in it. So if I want the complement of A, that means I want to have all of the elements that are not 1 or 2. In fact, I can even just kind of do this and get rid of them, and I'll cover them up so I can't see them. Now, everything else that's still here, everything else that I see is the complement of A. You can see we have the number 3 and the number 4 in this case. So the complement of A, which oftentimes we'll write like this with a little apostrophe, there's actually quite a few ways of writing it. Sometimes you'll see people write it like this, like A prime or A complement. Sometimes you'll see them write it with a little C above it. Sometimes you'll even just see people write not A, like that's a thing. Sometimes they'll do this little wavy line and put an A. There's a lot of ways of saying not A. I tend to do this, and this is one of the more common ways. So is the A complement. I don't know, they're all relatively common. In this case, because A was 1 and 2, whoops, because A was 1 and 2, A complement is going to be what we still have left. A complement or A prime would be 3 and 4. So those are not a part of A. They are the complement of A. Now, for something like this, you would actually need to be in a class. So the rest of these would just be things to do with the people in your classroom. I hope this helps a little bit. I would strongly encourage you to play around with these and make up some sets of your own to see what you think about A and A complement or A union B, etc. Some of the details can get a little bit tricky and they do require some practice. All right? Good luck.